Okay. So the first question is a very simple second order homogeneous differential equation. So whenever you see this type of differential equation, then the the simple things to do is just to plug in a Charles solutions. And for this for this type of equation, then that Charles solution will be simply um, a an exponential, which is e to the power st. And then after plugging in the Charles solution into the differential equations, then um, let me try to annotate if possible. Oh, this simile is not working. Well, anyway, so you just plug in the Charles solution into the differential equation, and you just do the derivatives. And then because the exponential term here cannot be zero, so you can just cancel it out from the equations 3 here. And then you have the quadratic equations. Then you just solve it, and you can to solve for the s, and the solution will be -1 and plus or minus 2i, and therefore the solution will be e to the power plus -1 plus or minus 2i t. And because either of the solutions um, are possible, and therefore a general solution of this differential equation is indeed a linear combination of these two solutions. So we have the C1 and C2 here. And if you prefer to write the exponential here in terms of sine or cosine, then it is also equally uh, well for you to write it in the form in equation 7, which is in terms of sine and cosine if you do not like the exponential here. Okay, and then for the second question, so for this question here, you have the inhomogeneous term here. Um, sorry, let me try to. Okay, and for this type of differential equation, and the general solution would be a superposition of the so-called homogeneous solution and also the particular solution. So which is a YH and a YP here. So the homogeneous solution means the solution will satisfy the equation 9 here. So we have the we have the inhomogeneous term here to be zeroed, and then for the particular solution here means it is any uh, solution that satisfy the equation 8 here. So as long as you find a solution that can satisfy this solution, and then the YH plus YP will be the general solution of this differential equation. So the very first thing we need to do is to solve for this homogeneous differential equation. So we just do the same thing that we have done in question 1. So we just plug in the Charles solution e to the power st, and then we just do the same thing, and then we can reduce the differential equation into a quadratic equation. Then after solving it, you should be able to find the s to be equal to -1 or 3, and therefore the general solution takes the form like this. It's a C1 e to the power minus t plus C2 times e to the power of 3t. And then the next thing is to find the particular solution. So uh, in order to have an educated guess of the particular solution, you have to observe the functional form of the inhomogeneous term here. So if it is an exponential function on the right hand side, then the possible solution for y should take the form, so suppose this one is a e to the power 2t, and then a possible solution would be also some exponential, which is also e to the power 2t, but it has a some scaling factor in front of it. And then what you have to do now is to solve for the d here. So you just plug in the Charles solution um, into the ODE, and then you solve for the d. So similarly, you can cancel the exponential term, and then you just solve for the d. And the d here should be minus 1 over 3. And then we just substitute the d back to our Charles solution here. Then this one is our particular solution. So the last thing to do is to add the homogeneous solution and the particular solution together to get your general solution. So this is the solution for 2A. And then for 2B, oops, I think there's a typo. So the inhomogeneous term here should be a polynomial. Um, but the left-hand side is still the same ODE that we have seen in 2A. So we have solved the homogeneous um, term already. And then now we just have to solve for the particular solution. So if the right side is a polynomial, then the particular solution should be also a polynomial with the same order. So this one is up to the second order, and then the particular solution should be also a polynomial up to the second order. So we just take the form as d times t squared plus et plus f. And then the next thing to do is to solve for the d, e, and f. Similarly, we substitute the Charles solution into the ODE, and then we just do the derivatives, and then we can just compare the coefficients of each term of the polynomial, so that you have a t squared here, then their coefficient has to be equal. And so we have the minus 3d equals to 3, and then we have the minus, for the minus 3e has to be equals to 4, and the 2d minus 2e minus 3f has to be equals to minus 5. Then after solving those or these linear equations, then you should be able to find that d equals to minus 1, e to be 0, and f to be 1. And therefore the particular solution is minus t squared plus 1. So the general solutions takes the form like this. So this one is just a homogeneous solution that we have solved in part A, and this one is a particular solution. Then for part C, and also if you have any questions, just feel free to interrupt me. So for the part C, so we have the same the, the left side is still the same, but we have a different particular, we have a different homogeneous term. So we do not need to solve for the homogeneous solution. We only have to solve the particular solution. So whenever the right side is some sinusoidal functions, a sine or cosine, then an educated cat an educated guess of the particular solution should also be some sine and cosine. And but so because on the right hand side there is second order derivative, and also first order derivative. So if the right hand side is cosine, then the particular solution would not be just cosine only, because if y is sine, then the first derivative will also give cosine. So it's also possible for y to have some sine term here. So the particular solution is indeed a linear combination of the sine and cosine. And then we just substitute the Charles solution into the ODE, and then we just solve, so after rearranging the terms, then because the cosine and sine, they are orthogonal to each other, and therefore for the cosine here, so you see the right hand side, you have the cosine term, so the coefficient has to equal, so the minus 3e minus 4d is equal to 2, but because there is no sine term here, so the coefficient here has to be equal to 0. And then lastly, you solve for the d and e, and then you should be able to get the d to be minus 8 over 65 and e to be minus 14 over 65. Then you just combine the results of the homogeneous solution and the particular solution together, then you can get the general solution here. So, and lastly, for the equation, for the question 3, so so you should recognize this differential equation to be in so-called Euler differential equations. So if you see the differential equation here, um, where the coefficients are some power of x, which the order match the order of the derivative. So this one is the second order derivative, and this one is x squared, and this one is first derivative of y, and this one is the um, first order power of x, and this one is zero order, and also you have the x to the power 0 here. So if the differential equations has this characteristic, then it's the so-called Euler differential equations. And for this type of differential equation, the solution will take the form like this. So it is just a power of x. So we just let the child solution to be x to the power r, and then we solve for the r here. So you can just substitute the solution into the ODE, and then you just do the derivative. And because here we have the x to be greater than 0, so the term here will not be 0. So it will be safe for us to just cancel the x to the power out here. And then what we have left is the quadratic equation. Then you just solve for the r. Then you will be minus 3 or 5 over 2. So because both solutions are equally good for the ODE, so the general solution would be a linear combination of both solutions. So you are also given the boundary conditions of this ODE. So in order to solve C1 and C2, you have to impose these two boundary conditions. So for the first boundary condition, you have y1 to be equal to 0. Then you just substitute x to be 1. Then you have c1 plus c2 to be equal to 0. And then second boundary condition is 1 prime of 1 to be equal to 1. Then you just do the derivative and substitute x by 1. And then you can get minus 3c1 plus 5 2c2. And this one is equal to 1. Then you can just solve these two linear equations, then you should be able to get C1 to be equals to -2 over 11 and C2 to be equals to 2 over 11. Then this would be the final solution. So do you have any questions? So just feel free to speak up if you will have any questions regarding the exercise. Alright, so if there's no questions, so let me answer the question from the link. So may I ask a question in Notes Chapter 1 classification? What if there are dependent variable in case 5? There are only two situations on Notes. So can you share um, share the lesson notes? I mean, you can just share screen and try to um, clarify your questions. And also, if you have any question regarding the lectures, you're also welcome to ask it here. Oh, so you cannot share. Okay, let me try to find the lecture notes. So it's chapter 1. Okay. Okay, I'll just share the stream. So I think you can try to speed up. So the question is in case 5. So which page is it?
That is page 6.
Page 6. Right. So your question is in case 5. Why can you try to illustrate your question, because you asked me properly, so other student may not really know what exactly is your question.
Okay, I mean, in this lecture notes, it only lists the case when constant coefficients or linear independent variables. But how about linear dependent variables in front of the unknown function or their derivatives?
Independent, then do you mean functions of dependent variable.
Yeah, in front of the ux or uy, the variable coefficient situation only lists independent variable. But how about they are linear dependent?
I think what it means here, so I think the dependent variable here is a u, right?
Yes.
So do you mean the ux, the coefficients in front of ux or ui is something, some functions of u?
Oh, well, maybe I have some misunderstanding. Let me think.
Because because the independent variable here actually mean x and y, and I think if you're trying to say some variable to be dependent, I think that would be only be u. Then you will say there is some coefficient that is a function of dependent variable. Then what I understand is something that is a function of u. So do I misunderstand your questions?
Well, let me think. So if we say dependent variable, that is just means u. I have I have thought that it may means x or 4x, 3x. This that is dependent. So maybe that is my misunderstanding towards this notes.
Okay, so no matter it's 3x or 4x, they are still functions of independent variables, which are x and y.
Okay, maybe I have some misunderstanding towards this note. Sorry.
Oh, never mind. Okay, so is there any other questions regarding the exercise class or the lectures, and also you're welcome to also give comments on how the exercise class should be conducted, because now everything is carried out online. So if you think there is a better way to to deliver the exercise class, you're also welcome to let me know. Then I may just try to improve the class in the next few sessions.
Well, may I confirm one thing?
Okay.
In Euler's equation,